Hello everybody, welcome to this lecture 4 of this course Optimal Control Guidance and Estimation. So far we have seen some overview of this course followed by some overview of topics related to systems theory as well as matrix algebra and numerical methods as well, that is relevant in this course actually. So, and another thing that is very much relevant in this course is the concept of static optimization. That means, we are not talking about time varying variables and all, but these are constant numbers associated with that. But in general they have some objective and all that, how do you optimize that actually? Okay, so that kind of things are called static optimization, or sometimes it is popularly known as parameter optimization as well, because parameters are something that typically remain constant actually. Okay, so anyway, so those are the topics of discussion of this particular lecture. And also remember, as I told you in the beginning lecture, the very first lecture, that one way of solving this optimal control problem is to go heavily to this static optimization ideas and convert the problem entirely to a large dimensional static optimization problem and solve it. That is called transcription method and all. We will see that as the course develops. Another motivation of that is, even if you formulate this optimal control problem from calculus or variation point of view and all that, you essentially land up with some equation something called Hamiltonian and all that, and that happens to be like every point, it happens to be kind of a constant quantity in its variables state and control, and that you need to minimize at every point of time in the framework of static optimization actually. This is very relevant concept for optimal control in general. So, it obviously makes sense to have an overview of static optimization before we go to the dynamic optimization, that means optimal control synthesis and all actually. So, this I will take it in two parts, and the first lecture will talk about some overview or some standard results of static optimization along with some examples and all that way. Then further topics on it we will see in the next lecture, and before proceeding to the calculus of variation ideas and all that way. Okay, so, the topics of this lecture is something like this. We will first discuss about unconstrained optimization. Then we will go to this constraint optimization with equality constraints primarily. Inequality constraints and all we will see in the next lecture actually. Okay, then we will see some numerical examples as well. Alright, so first is unconstrained optimization, and the problem definition turns out to be very clear, that you want to optimize some function of variables, but the variables are combination of some non-time varying quantities actually. Okay, so that is they are not constrained by any constant equation either actually. Before proceeding with the algebra and then analysis and things like that, let us see a very simple straightforward idea first actually. Now, forget it for a second, this J2 dotted line and all, this plot was x versus some function J1, let us say, and J1 turns out to be this function, this solid function actually. And then very quickly we can see that this point 1, 2, 3, 4, they mean something to us in just by looking at the plot actually. And very easily it can be argued that this point 1 happens to be a local maximum, and point 2 is, well, we can't say anything about that, it is a flat thing, but certainly a candidate for getting worried about. And then it is called point of inflection and all that, and then point 3 turns out to be a local minimum, and point 4 turns out to be local maximum. Just by looking at the plot we can very easily see that this is what is happening actually. And then it also we can see that point 3 turns out to be global minimum and point 4 turns out to be global maximum, because nothing else is bigger than that in this domain, of course, I mean xi to xb and all that way. But when you talk about global maximum and all, typically this xi and xb are also not there. In other words, you talk about minus infinity to plus infinity, that domain sort of thing actually. But anyway, within this constraint, then you can think that, okay, 4 happens to be the global maximum and 3 happens to be the global minimum actually. And one property that we observe, simply observe, is that all these points 1, 2, 3, 4, this relationship is true. That means the gradient of j with respect to x is 0. If I just take a tangent here, that is flat, this is anyway flat. If I take a tangent here, it is flat, and then it is if I take a tangent at the 4th point, then they also parallel to the x axis actually. So, all the points will satisfy that. Now, that gives us a clue that when you talk about something about optimization, then obviously the first derivative should happen to be 0, that is our intuitive guess actually. Now, does it really happen? So, let us talk about that way, and also remember that instead of J1, suppose you have J2, okay, then we really do not have to worry about all these, you just have to worry about one minimum, okay, that is what all that it will have is one minimum, and that one minimum happens to be the global minimum as well actually. Okay. So, most of the time we will take advantage of this observation, and while we construct a function, we will want to construct it that way. So, that we really do not have to bother about global things and all, it is not relevant also, most of the time it will satisfy our need also basically that way. This is quadratic function and all that we will talk later. Okay. So, this is how it turns out to be. Now, coming back to that, whether this relationship satisfied for all the points and all, analyze it little bit mathematical rigorous sense basically. So, now again we go back to this Taylor series and all, which will repeatedly require anyway. Now, remember what is a local maximum? Local maximum tells you that if point 1 is a local maximum, then very next to it, whether you go left side or right side, either way, that will give you a function value which is lesser than the function value at point 1. Similarly, if it is 0.3, if it is a minimum, local minimum, then whether you go left side or right side, either direction, you are going to get higher values than what you get at 0.3 actually. Okay. So, that kind of concept is there. So, let us analyze a point x star and then talk about a value of that function around x star, and remember delta x can be either positive or negative actually here. Okay. And also remember we are simply talking about a scalar quantity, that means x is just a single single component, j is a function of x, but x does not contain x1 x2 components and all that, x is just a scalar variable sort of thing. Okay. Then what happens, x star plus delta x minus j of x star, that is the term what will come from Taylor series like this actually. Okay. Now, for any hope to have, so what we are looking for? We are looking for this quantity j of x star plus delta x should be greater than j of x star, okay, if j of x star happens to be a minimum point, irrespective of the direction of delta x or the sign of delta x really actually. Okay. So, if that has to happen, that means this left side quantity has to be strictly positive for this quantity to be kind of local minimum, or it has to be strictly negative for the other case actually, local maximum case. So, what you are looking at here is a sign independent property really. Okay. And also remember this Taylor series has this uniform convergence property and things like that. So, that means if you write this expression to be something like that, if you take this entire quantity, what turns out to be like this, okay, the infinite terms what you are talking here is less dominant compared to the first term actually. Okay. So, that is how it will turn out to be. So, in other words, the sign of it is largely dictated by the first term itself actually, yeah, and not by these terms actually that way. So, if you have any real hope of that this becomes sign insensitive, then it turns out that the first term must be going to 0, then only we have some hope actually. Okay. Now, that is how the necessary condition turns out to be, and remember delta x is not 0, so, but this quantity has to be 0, that means the coefficient has to be 0 basically. So, that is how it turns out that if del j by del x at x equal to x star is 0, then x star happens to be a candidate point. I mean, we still cannot tell whether it is minimum or maximum actually. Okay. So, for that we will go to the next one and then tell, okay, if that is already there, that means at this point this is 0 anyway, then this quantity turns out to be that one, and that one means I can consider the second order term, and then there is a still higher order terms from third order, fourth order, I can neglect actually. Okay. So, if this still has to be positive, that means this has to be greater than this irrespective of the sign of delta x. Remember, this is a square term now. Okay. So, this has to be strictly greater than 0 provided this is greater than 0. Okay. Now, this is greater than 0 anyway. Okay. So, this quantity is greater than 0 provided this quantity happens to be greater than 0. That means, second order term has to be greater than 0 basically. And similarly, if the second order term happens to be less than 0, it will lead to the conclusion that this term is less than 0. In other words, this term happens to be a maximum actually, the x star happens to be a maximum. So, this is how the analysis. So, to summarize the things, what we are doing here is given any function j of x, we will put this del j by del x equal to 0 and then solve this and find out candidate points x star, need not be one point, it can be several points actually, and at each of the points we will try to evaluate the second order derivative. Okay. And the second order derivative happens to be 0, then it is a minimum point. The second derivative happens to be less than 0, it is a local minimum. That is the sufficiency condition actually. So, before carrying out further things and all, let us see this some example sort of thing. And even before the example, okay, Now the question is what if this both the derivatives are 0, but the third order derivative is not 0. Okay. So, that means this is true whatever we talked about only if the second order derivative is non-zero. Okay. Now, if the second order derivative also happens to be 0, then we have no choice but to go to the third derivative, and the third derivative happens to be non-zero. Okay. Then we really cannot tell whether it is strictly positive or strictly negative, and hence it turns out to be a point of inflection actually. Okay. And if it is just, I mean, if you still have a hope of getting it something like a positive or negative, you must have the third derivative also 0, and then go to the fourth derivative and things like that actually. Okay. Right. If it is second derivative is 0, then this lands up with the third derivative case, and then there is a necessary condition of optimality is if you still have any hope, then third derivative is to 0, then you will end up with fourth derivative. And if the fourth derivative happens to be non-zero, that means positive, then it leads to minimum and maximum, and otherwise it is maximum actually. So, the analysis continues, it actually toggles between this odd power and even power sort of thing actually. So, as a necessary condition all odd powers has to be 0, and sufficiency condition will come from even powers actually. Okay. So, this is how the things proceed, and suppose we want to get an example here, then it turns out to be, let us take a very simple example, j equal to x fourth, and you can see that well, the x fourth plot is very close to this kind of okay, very similar to x square sort of thing. So, obviously, we know that this is the point of minimum, that means x equal to 0 is the answer, we know that actually. Okay. So, whether you get it or not, let us see that using these results. So, if you have j something like this, okay, then del j by del x is 4x cube equal to 0, okay. Then your solution of that is 3 quantities, but all happens to be 0, that x star equal to 0 0 0. And then okay, let us go to the second derivative, and second derivative turns out to be like for taking this term it is 12 x square, and x star equal to 0 means 12 x square is also 0. So, we really have to go to third derivative now. Then the third derivative fortunately happens to be 24 x from here, 12 into 2 24 into x star. So, x star is 0 anyway. So, the third derivative is also 0. So, that means there is still our hope is alive actually. Then you go to fourth derivative, and fourth derivative happens to be 24, which is greater than 0. Okay. So, if the fourth derivative is greater than 0, then obviously it tells you that okay, my sum of my all of my odd powers are 0, and the first even power that I encountered is actually greater than 0. So, obviously, x star is a minimum point actually. That is how you conclude that the result is compatible to what we know actually from graphical sense. Now, example 2, what if x is j is just x cube, and remember x cube what is the type of I mean thing plot, x cube is something like this, if it is positive is positive, if it is negative is negative, something like this. So, here we have a point of inflection really, that means at 0 what you are talking here is one side the second derivative will turn out to be, I mean one side the function turns out to be increasing, other side the function turns out to be decreasing actually. So, this is we know that it is a point of inflection. Now, whether our analysis tells that or not, let us see. So, if you have j equal to x cube, then del j by del x is nothing but 3 x square equal to 0. Okay. So, x star turns out to be 0 0. Okay. Now, you have two candidate solutions, but both happens to be identical anyway. Now, the second derivative happens to be 6 x square is also 0. So, we cannot conclude anything this point of time, because this is 3 x square. So, it will be 6 x. So, 6 x evaluated at x star, that is 6 x star is 0. So, it is still 0 basically. Now, we have to go to third derivative, and third derivative del q j by del x cube coming from here is nothing but 6. But the important point to note here is not whether 6 is positive or negative, but 6 is not equal to 0. Remember, it is a third order derivative actually, okay, odd power derivative. So, this odd power derivative has to be not equal to 0, that is more important actually. If it is not equal to 0, your hope is not alive, your conclusion has already been there, and the conclusion is the x star is a point of inflection, because if I take this series, okay, this term will start dominating, and if delta x is positive, okay, depending on whatever sign is there, it will lead to one sign, and depending on whatever sign is there here, if delta x is negative, it will lead to exactly opposite conclusion here. So, it's just one side it is either increasing or decreasing, but the other side it is just the opposite actually. So, this will turn out to be point of inflection. So, that is how it is there. So, if j equal to x cube, then x star equal to 0 turns out to be a point of inflection point actually, a point of inflection really. So, it is all compatible to what we know basically. Now, but this is not end of the story, this is just very beginning, it talks about a scalar variable function sort of thing actually. But we are not interested in a scalar variable function in general, because we deal with systems theory where states can be n dimensional, control can be n dimensional like that. So, it is a mixture of these components of the state variable really. Okay. So, that is what we want to analyze, then it leads to this vector case. Okay. And the problem is turns out to be like that, minimize j of x where x is a n dimensional vector. And remember, the objective function is always a scalar quantity, unless otherwise you talk about multi-objective optimization and all that. We are not talking about that at all in this course actually. So, when somebody talks about a standard optimization problem, then it turns out to be that the optimization function is a scalar quantity. Okay. Whereas, the variables can be n dimensional, there can be several variables playing out different contributions and all. We want to minimize this scalar quantity finally. And also remember, this is an unconstrained problem, that means this component of x are not constrained by any constraint actually. Okay. They can take any values whatsoever actually that way. So, we want to analyze that problem and see what is going on actually. Okay. And also remember, by definition what we saw on this matrix theory reviews and all that also, that by definition this is del j by del x equal to like this. Okay. By this is nothing but the gradient vector, and del square j by del x square Hessian matrix turns out to be like that by definition actually, and these things we will need. Okay. Now, again going by the similar concept this optimization ideas and all, now we are asking a question that we want a value x star, where from x star you do go whatever direction you want, okay, no matter whatever direction, left, right, top, bottom, whatever it is actually, whichever direction you go, you will get some value which is strictly greater than the value at x star. Okay. Or you will get a value which is all of which are strictly less than a value of j x star basically. Okay. Then only you can talk about whether it is a minimum or a maximum quantity sort of thing actually. Okay. And pictorially again, if somebody wants to picture, then in a 2D sense you can think about this kind of a picture. Okay, this is not this kind of a picture actually. So, if you have a minimum point somewhere, no matter which direction you look at it, okay, you can think of it something like a increasing function in all directions sort of thing. So, no matter which direction you go in, okay, you will end up with higher values compared to the minimum point actually. Okay. So, that kind of questions we are talking about actually. So, again going back to this idea of Taylor series, we know there is this vector variable also we can use this Taylor series expansion. So, we talk about j of x is nothing but j of x star, which is x star happens to be a candidate point to analyze for maximum or minimum, and then j of x star plus delta x can be expanded that way. Okay. Remember, this is the first term j of x star plus the linear term del j by del x evaluated at x star into delta x, plus this second order term which is 1 by 2 factorial delta x transpose into this Hessian matrix times delta x, and then higher order terms actually. Okay. And in this case, we will not be very adventurous to go to this third order, fourth order derivatives and all that. It is still possible to write, but mathematically they are quite complex actually to write in Long-Hand algebra sort of thing actually. So, let us see the idea first in this context, and most of the time this is sufficient for us also basically. Okay. So, for minimization problem, what you are looking at is this quantity, this j of x star plus delta x minus j of x star, that quantity has to be strictly positive. That means, no matter which direction you go, the delta x can be any direction, okay, component by component, they can take any positive, negative, any quantity whatsoever actually. Then it turns out that, okay, if my value turns out to be higher than that, then it is a minimum point actually. Okay. So, obviously, if I want to satisfy this, then again going by this idea of direction sensitive information and all that, we can always tell that, okay, if my hope is alive, that means I really want to conclude have a conclusion something like that very precisely, then it turns out that this term what you see as first order term has to be 0. Okay. Otherwise, if I have something non-zero here, okay, the coefficient sense, then depending on this quantity delta x, which can be positive, negative, whatever component sense, I will end up with an idea of this quantity can be either positive or negative. So, it becomes direction sensitive actually, and which we do not need. Okay. So, it turns out that, okay, if you really want to have a minimum point, then this first order Jacobian matrix, Jacobian vector rather, sorry, it is gradient vector. So, gradient vector has to be 0. Okay. So, that this multiplication has to be I mean turns out to be 0 basically. Okay, this is a small probably a print mistake sort of thing. Okay, this has to be transpose actually. Because we talk about this del j by del x being a column vector and all that actually. So, the multiplication will be defined only when it is a row vector actually. Okay. Anyway, so this is what it is. So, del j by del x evaluated at x star transpose and things like that actually. So, for minimization again to summarize, for minimization we want this to be strictly positive. So, the necessary condition turns out to be something like this, and the sufficiency condition again going by the earlier idea. So, once this is 0, we will end up with this term, and this term has to be positive, strictly positive for all delta x non-zero. Okay. And if you remember this del square j by del square, once it is evaluated at x star, it is actually nothing but a matrix of numbers basically. Okay. So, this matrix of numbers multiplied with some vector transpose and right multiplied with the same vector with non-trivial vector and all that, it has to be strictly positive quantity. That means, by definition of what we saw in matrix theory, the equivalent idea is this matrix what you are seeing here by definition has to be positive definite. Okay, because the positive definite definition tells us that anything that we pre-multiply with some vector transpose and post-multiply with that same vector, okay, which is a non-trivial vector, and that has to be strictly positive for all such vectors basically. By definition, this in that case, this matrix turns out to be positive definite. So, and also remember positive definite is tightly linked with the eigenvalues and all that, and del square j by del x square is guaranteed to be symmetric matrix. That means, the eigenvalues are guaranteed to be real. So, if it is real and it is all eigenvalues are guaranteed to be greater than equal to 0, because it is a positive semi-definite, I mean sorry, I am take it back, this is a symmetric matrix. So, eigenvalues are all real actually. Okay. Now, it turns out that if it is a positive definite matrix, okay, by this analysis that I just told, then eigenvalues are going to be all positive actually. Okay. So, just by looking at the eigenvalues of this matrix, because it is a constant matrix after getting evaluated at x star, if all eigenvalues are guaranteed to be positive, and remember it is guaranteed to be real in any case, okay, then it turns out to be positive definite, and if it is positive definite, then this term turns out to be strictly greater than 0 for all possible delta x, no matter whatever direction of delta x is, and then hence this relationship will be valid actually. Okay. So, as a summary, what turns out that the necessary condition which can be given like this, that means your gradient vector evaluated at x star has to be 0, and then whatever candidate solution you get from there, you go to the sufficiency condition and tell, okay, if I evaluate this Jacobian matrix at values x star, all possible values x star, and then I see whether the Jacobian matrix turns out to be positive definite or not actually. Okay. And if it is positive definite, the x star is a minimum solution. If it is negative definite, on the other hand, it is a maximum solution actually. And also, as a remark, further conditions like third order, fourth order and all are difficult to use in practice, and typically it is not required as well in most of the applications actually. Anyway, so this and rather most of the engineering applications, I will say that way. Okay, then many times we will end up with such cases that it turns out that first order and second order turns out to be sufficient actually. But that does not mean that the mathematically we cannot develop further and all that actually. That can always be there basically. Anyway, coming back to the example, suppose we take an example of 2-dimensional case now, half of x1 square plus x2 square, we want to see where the minimum lies and all that way. Then as a necessary condition, I will first go through that, this del j by del x, I will evaluate at x, I will put it at equal to 0. Remember, this is a vector equation, that means it has two equations actually embedded in that. So, essentially it tells you that del j by del x1 and del j by del x2 equal to 0 0. But del j by del x1 from this expression is nothing but x1, and del j by del x2 is nothing but x2. So, evaluated at x star, that means the star things and all. So, this has to be 0 0. That means, as I told again, this pictorial representation is what I have shown you already. Okay, this is pictorially we know this result actually. Okay, in x1, x2 and things like that. This is j. Okay, and we know the solution already here actually 0 0. Okay, turns out to be the same actually from the math. Okay. Now, the question is, can we verify sufficiency condition? The answer is very much yes. You can go to see once we have the gradient vector, we can talk about the Hessian matrix actually. So, del square j by del x square evaluated at x star turns out to be something like this, and remember this is the gradient vector. So, take second order derivative, this variable, okay, this is only x 1, this is only x 2. So, if I take with respect to x 1 one more time, I will get 1. If I take derivative with respect to x 2, there is nothing there because it is a function of x 1 only, so that is 0. Similarly, if you talk this one, this turns out to be again the only function of only x 2. Okay. So, if I take partial derivative with respect to x 1 again, then turns out to be 0 here, and if I take x 2, this is 1. Okay. So, this Hessian matrix evaluated at x star turns out to be nothing but identity matrix actually here. Okay. So, identity matrix is certainly a diagonal matrix, and we all know that eigenvalues are all diagonal entries actually, nothing but 1 1 1 and all that actually that way. So, the eigenvalues of this particular Hessian matrix is nothing but 1 and 1, both are greater than 0, and hence this matrix evaluated at x star, which is 0 0, this matrix evaluated at x star happens to be a positive definite matrix. Okay. So, what it turned out to be, like we got a solution 0 0, a candidate solution, and the second order analysis, that means the Hessian matrix evaluated at that point happens to be strictly a positive definite matrix, because all the eigenvalues are strictly greater than 1, greater than 0 basically. Okay. So, because of that this point is guaranteed to be a minimum point. It satisfies both necessary condition coming from here and sufficiency condition coming from here, which tells us that it is a diagonal matrix, and hence it is eigenvalues are diagonal entries, positive numbers, hence it is a positive definite matrix basically. Alright. So, let us move further, and what if this kind of an example instead, x 1 square minus x 2 square, then the ball game is completely different, and it turns out to be similar algebra, you get a candidate solution as 0 0. However, when you go to the second derivative, it turns out to be 1 and minus 1. Okay. So, the eigenvalues are 1 and minus 1. So, it is really neither positive definite nor negative definite, but strictly speaking you can think, okay, if I go along x 1 direction something happens, if I go along x 2 direction exactly the opposite thing happens, and typical example is this I do not know, this horseback and all that they talk about it. I mean this seat on the horseback and all that. So, that picture really I do not know, can I write it that way? So, this kind of a thing, the function will decrease this way, and this will increase the other way around actually. Okay. So, if you imagine something this direction, the function will decrease, but this direction the function will increase sort of thing actually. So, this is the case where you talk about not a point of inflection, because that is the idea of a scalar variable. So, here it is something called a saddle point actually. Okay. So, this is the point where in one direction, in x 1 direction things will increase, but in x 2 direction the function will decrease actually. Okay. So, in this case it mathematically turns out that del square j by del x square evaluated at x star is neither positive definite nor negative definite, and hence but the first gradient vector is 0 0 anyway. So, in such cases this is nothing but a saddle point actually. Okay. Now, moving on, what about constraint optimization, and then when you talk about free optimization like this, what you saw there, again these are not very meaningful thing, because most of the time will be constrained by some relationship between the variables, and again I will keep on emphasizing that in optimization and optimal control everywhere, constraint has the priority actually. Okay, that means your solution will have absolutely no meaning if it does not satisfy the constraint. So, you have their constraints, first you satisfy the constraint, and within that constraint only you try to optimize actually, and in general it happens in real life as well actually. We have to cater for constraints first, and then talk about optimization around that basically. So, that is how we are dealing with, and when you talk about constraints, the constraints can be of two types, one can be equality and inequality, and the other can be inequality. And then in this particular lecture we will see about equality constraints, and then inequality we will talk about that in the next lecture actually. So, the analysis goes to be a little more complex and things like that way actually. But also remember, as a combination of equality and inequality constraint is what will happen in real life problems actually. Okay. So, we should know how to handle equality constraints, and we should also know how to handle inequality constraints as well in general basically. Anyway, so let us talk about equality constraints here. Okay, the problem formulation is like this. We want to minimize some j of x, again always j is a scalar, but x is a vector. Subject to this is set of equality constraint, it is not just one constraint actually, remember that. So, this equation actually is m equations, because f has components f1 to fm. Okay. So, now this is the problem. We want to minimize a scalar quantity of a function where the function itself is n dimensional, and that is subjected to m constraints, actually m algebraic constraints. Okay. Now, the solution procedure relies on this so called Lagrange existence theorem and all that, which tells us that if I formulate another cost function like this, okay, or another this objective function and all that, j bar, which is nothing but j of x plus lambda transpose f of x. Okay. So, the theorem tells us that if I introduce a function like this and interpret, okay, for a second you forget that f of x equal to 0, that means this is 0 anyway, basically no matter what. But for a second you can forget that, and then tell, okay, what if lambda is a free variable and I do not worry about this constraint really, but I just want to put this f of x here and I want to minimize this function rather j bar of x, okay, considering lambda as a free variable actually. Okay. And also, okay, just a small comment before we move ahead, most of the time I will talk about minimization, and most of the textbooks and most of the lectures will also talk about that, different courses. The reason here is if something we want to maximize, the negative of that is something that we want to minimize basically. So, just by introducing a negative signs, the minimum can be interpreted as maximum and vice versa actually. So, it does not have that much of a great importance to segregate this and talk segregation sense all the time actually. So, we will confine ourselves to discussions around minimization all the time without loss of generality of course. Anyway, so coming back, this is the theorem which tells us that if I formulate an augmented function like this, that means j bar equal to j plus lambda transpose f, okay, then if I consider j bar as a function of x and lambda both are equally free basically, and I consider this as a free optimization with respect to x and lambda both, okay, then it is equivalent to solving this optimization problem subject to this constraint. This is a great theorem. I mean, this it's a little bit math heavy also, but those of you are interested can see some vector space optimization books and all that way. We will not go to that much of thing. Again, this course is primarily meant for engineers and engineering flavor and all that way. So, let us come back to that. The theorem essentially tells us that if I constitute a j bar like this, j plus lambda transpose f of s, where lambda is a set of free variables, and again I am emphasizing because similar concept will use in optimal control also basically. Okay. So, if I constitute this function and consider this as a free optimization problem in terms of x and lambda both, then it is equivalent of solving this problem. This is j of x minimized subject to this actually. Okay. So, using that, this gives us a solution procedure, and the solution procedure tells us that, okay, first you formulate this j bar, okay, like this, and then carry out it as if it is a free optimization problem. And remember, the number of variables are now x and lambda, that means I have to satisfy simultaneously this del j bar del x equal to 0 and del j by del lambda also equal to 0. Now, when you talk about del j bar by del x, it turns out to be from this definition, this is nothing but del j by del x coming from this term and the second term. Okay. And remember, if you do this algebra del j by del x of this using this one of the standard results of this vector matrix calculus that we discussed in the review class before this lecture, then it turns out to be del j by del x of this happens to be this result actually. That means, this derivative del f by del x transpose happens to be in the left hand side, it will shift from right hand to left hand actually. Okay. So, this is how we will get it. Okay. So, del j bar by del x is this one equal to 0, and remember lambda is also a free variable, that means del j bar by del lambda is equal to 0, but what is del j bar by del lambda by definition? Okay, this is nothing but f of x. So, f of x equal to 0 which came from here is part of the necessary condition anyway. Okay. So, we are accounting for the constraint, but that is how it is equivalent actually in a way. Okay, that way. So, what you are doing here is this one del j bar by del x which is equal to 0 and del j bar del lambda which is also equal to 0. This will give us an n equation and this will give us m equation, because lambda is m dimensional, remember that. This lambda is same dimension as f is m dimension actually. So, this is actually leads to something like an n plus m equations in n plus m variables basically, and these are n equations, these are m equations. So, totally n plus m equations, and free variable sense we have x as n dimensional free variables and lambda as m dimensional free variables. So, we have this n plus m variables actually. So, we have a compatible set of equation, we need to solve it together, and also after the solution, after we get the solution, we typically are not bothered about lambda, we are bothered about the value of x actually. Okay. So, this is something like can think of it as something like a catalyst operator in a chemical reaction and things like that way actually. So, catalyst itself kind of facilitates the reaction, but ultimately the catalyst is not a product that you are interested in and all that actually, but without that you cannot carry out the reaction properly many times. Okay. Anyway, so this is how it is. So, let us go to an example again. So, we want to minimize the same thing whatever example we saw before, but not as a free optimization problem, that we know that 0 0 happens to be the solution, but this time it is constrained to a linear equation, let us say x 1 plus x 2 equal to 2, that is nothing but something like a surface, something like a plane equation sort of thing actually. So, this example that I gave you here, this one is now subjected to, I do not know the what way it is inclined, but let me just conceptually draw one. Okay. This is a plane that we are talking about, and this plane actually this plane goes and cuts this I mean this paraboloid and all that way. So, we will end up with something like a inclined parabola sort of thing, and then in that you talk about what is my maximum minimum value actually. I am not interested in 0 0 anymore. Okay. So, this is the type of problem that you are interested in, and then the result turns out to be, I mean the procedure turns out to be like that. J bar we constitute first. So, this is coming from here, followed with, remember this only one equation, this is one single lambda again. So, lambda into this f of x, this is my j bar, and first I have to do del j bar by del x, and these are two equations here because x contains x 1 and x 2. So, it is del j bar by del x 1 equal to 0 and del j bar by del x 2 equal to 0. Then the third equation has to be del j bar by del lambda, and lambda is scalar here. So, del j bar by del lambda is nothing but that is equal to 0. So, you carry out this algebra del j bar by del x 1, okay, if you see this expression, one is coming x 1 is from here, and then this one more term here. So, this is lambda star lambda here, and of course, from here to here we change sometimes these star notations and all, because these are candidate solutions, these are generic expressions and all that. So, do not get confused that way. So, you get del j bar by del x 1, this term coming from here and this term coming from here, that is equal to 0. Similarly, del j bar by del x 2, this term comes here, and then that term, because of that term it will come here, both are equal to 0. And then del j bar by del lambda, if I talk about this expression, lambda means I get this equation. So, x 1 plus x 2 minus 2 equal to 0 sort of thing. So, I have to solve these three equations with three unknowns now, x 1 and x 2 and lambda. So, if I go ahead and solve it from these first two equations, I get this kind of a relationship, and from the last equation if I put it back, then it turns out to be that lambda star is nothing but minus 1, and hence x 1 star and x 2 star both happens to be 1 1 actually. And that also happens to be kind of, if you imagine a little bit here, then okay, I do not know, it requires a little bit imagination and all that, it depends on the plane inclination and things like that. So, this point what, okay, sorry, okay, this point happens to be our point, but this is a projection. If you take it here, something like this 1 1 will come actually. Okay. Okay, so, this is depends on the plane inclination, with what inclination the plane cuts the paraboloid sort of thing actually. Alright, so that is that's the kind of relationship what you are looking for. Now, okay, generalizing this results a little bit further, you can also think of minimizing some sort of a generic expression where a and b variables can be thought about as weighting parameters and all that, and subject to a generic straight line kind of not straight line, generic equation of plane sort of thing actually. So, where this if this in these expressions where a, b, c, m and c, all these are kind of constant quantities, but if you take different numbers you get different solutions ultimately actually. So, this is a kind of generalization of what we saw here actually that way. So, again you can go back and solve it, j bar is nothing but that, and then I can have a lambda plus this quantity, and then I can carry out with the algebra, same algebra, del j bar by del x 1 that turns out to be like that equal to 0, del j bar by del x 2 turns out to be like that equal to 0, and del j bar by del lambda will give us the same constant equation, that is also equal to 0. So, you solve it in a generic sense, and the solution turns out to be like that. And also a small comment here that lambda star has no physical meaning, and it helps, as I told, to solve the problems actually. Okay, that means you can think of it as something like a catalyst actually. But also remember, without this lambda we may not be able to solve this problem in a very good way though. Of course, we can talk about numerical solution and all that, but whenever you have a closed form expression, obviously we do not want numerical solutions either actually. But anyway, numerical ideas, philosophy, a little bit of that we can see it in the next lecture actually. Let us not go to that part of the story there. Now, what about sufficiency condition? I mean, these are all necessary conditions anyway, and I will not go into the derivation part of it, but it turns out that you formulate this matrix, what you see here inside the determinant. Okay, we talk about a second order matrix, I mean of J bar, remember that is Hessian matrix for J bar in terms of only x. Okay, then minus I sigma, this is a matrix by itself, and essentially what you are doing here is creating a matrix out of this partition matrices and all that. I can think of putting a partition matrix here, okay, like that, and I constitute this I mean this components individually. This is a matrix or rather a submatrix, this is a submatrix vector sort of thing depending, or matrix depending on number of f and x. Remember x is always a vector, but f can also be a vector. If f is a scalar and a vector, there are different meaning, and sometimes this transpose you will see it here depending on the situation actually. Okay, but essentially you constitute or create these components and put them together like this, take a determinant and make it equal to 0, and interpret everything else is known, because you already have a solution known to you by that time, x star, lambda star, all that is known to you. The only thing that is unknown is sigma actually. Okay. So, interpret this equation as a equation for sigmas, and then if sigma has all positive roots, when all such sigmas are positive, then it leads to minimum, and all such roots are negative, then it turns out to be maximum actually. Okay. And again the proof part and all I will not go into that actually. So, we will just take it on the face value sort of thing. Okay. But example we will see, okay, and we will go back to that example. So, very similar example actually. We will take this quadratic function followed by this constraint. This constraint is actually nothing but equation of a plane. Okay. So, solution approach is again very similar to what you have done before. So, if you constitute J bar and then talk about these equations which comes from del J bar by del x1 equal 0, del J bar by del x2 equal to 0, del J bar by del lambda equal to 0. So, once you have with this equation, solve it, and you can just carry out the solution yourself probably, because x1 has to be minus lambda, x2 is plus lambda, you substitute here minus lambda, and then it is plus lambda. So, it is minus 2 lambda minus 5 sort of thing. So, lambda happens to be minus 5 by 2. And x1 happens to be minus lambda, so 5 by 2, and x2 happens to be plus lambda, which is minus 5 by 2. Alright, so this is how you get a solution. Now, the question is how do you go ahead and test it for the sufficiency condition basically. So, this is where we will try to venture into this formula, whatever you have here, and this turns out to be like okay. So, this is del square J by del x square happens to be identity matrix, we have seen that before, and del J by del x equal nothing but 1 minus 1. Okay, because del f is here, del f by del x1 is plus 1, del f by del x2 is minus 1. So, put them together is like this. So, I go back to this formula and tell okay, this is what I will put it here, okay, and this is one. Remember this formula what I gave you in general, it is when f is vector and x is vector, but here we have f is scalar. So, this transpose is not necessary, I mean in fact this transpose come here actually really. This will become a column and this will become a row sort of thing actually. Okay. And that essentially comes from the definition. If you go back to this Jacobian and gradient vector and all that, if it is gradient vector it is column vector, if it is Jacobian vector, Jacobian matrix, it the similar partial derivatives are aligned in the row sense basically. That is from that definition this difficulty comes actually in a way. But remember, if it is both are, I mean if f is a scalar, then this transpose gets shifted here. Okay. So, with that assumption we will just see that okay, whatever these components are available. So, this will come here, okay, and the transpose of that will come here, okay. 1 minus 1 is here and 1 minus 1 will come here that way. So, now we have a determinant equation here, and if you carry out the determinant and then turns out that it is a quadratic expression, 1 minus sigma whole square equal to kind of 0 it will turn out to be actually. Okay. So, then sigma is nothing but 1 sort of thing actually, and both are happens to be positive. So, hence this theorem tells you that if all the roots are positive, then it is a minimum, and hence whatever solution you got here, this 5 by 2 minus 5 by 2 point happens to be a minimum point actually. Okay. Also, just a small comment, if this is actually the point that you are getting actually, okay, in a picture sense, this is what I showed you here. What you are getting here is the point. Okay. But if somebody asks you what is the value of that particular function at that point, then you have to go back and evaluate this j of x and get a value for that. Okay. So, that is we implicitly assume actually that is possible, because it is just a simple evaluation of the function that you. Okay. Some remarks associated with this example. In this example, these variables x1, x2 and lambda do not appear in the equation for sigma. Okay. Whatever sigma is there, it is independent of that, and hence it really does not depend on which operating or which candidate solution you are talking about, and hence this result happens to be global actually. Okay. And this solution is the only solution, in that sense also it happens to be global actually. In general, however, sigma will be a function of x and lambda, and hence the various conclusions that you have seen here, okay, in this sense, it can depend on which candidate solution you are talking about. So, around each candidate solution you have a set of sigmas, and this set of sigmas has to satisfy certain condition, like that actually. So, that analysis goes that way, and we will also give another example to demonstrate that actually. So, this is what the example is. Okay, this okay, in the constraint optimization sense, in sufficiency condition sense, we will go this another example like that. So, if it is like this, okay, and subject to this, this is a nonlinear equation, remember that it is not a equation of a plane anymore, but probably something like a equation of a kind of a sphere actually. Okay. So, then this particular value, I mean what you are talking about, what you are talking about is analyzing this particular problem. So, we will go back and formulate j bar is nothing but this plus lambda into that, and then carry out the necessary algebra, and then like will end up with some candidate solution, but going ahead we will need this del square j bar by del x square and all that, it will turn out to be like that. So, del f by del x also, if you see this, turns out to be 2 x1 and 2 x2 actually. So, now you put it back here, all the necessary condition will be like this, and because it is a nonlinear equation sitting here, and also this also is a nonlinear term, this also a nonlinear term, remember that, we will certainly have multiple candidate solution, and this candidate solutions turns out to be 4 candidates, okay, and these 4 candidates happens, you can quickly verify also, you take this set of values and then put it, you will satisfy all the equation, you take this one and put it, it will satisfy actually. So, that way. But in a solution sense, we really need to solve it and get some candidate solutions, all possible solutions actually. Okay. Now, it turns out that at each point we have to evaluate what the sigma values are, okay, and for that we have to do this okay. For that we have to take one particular thing and then go back to this, what is okay, this go back to this and then put it back here and then try to analyze what sigma values are those. Okay. So, that sense actually it happens to be. So, let us talk a little bit on okay, that part of it. Right. Okay, just to okay, before, well, we will talk about that, but just to demonstrate your confidence and all, let us talk about a verification of this this set of solution probably. So, we talk about 1, 0 and half. Okay. So, if I take this is like 1, okay. So, this is 1, but this is minus half actually here. Okay. So, minus half into 2 basically. So, this is happens to be minus half into 2, so minus 1 multiplied with 1. So, it is still minus 1. So, 1 minus 1 is 0 basically. Okay. Now, what about this equation? Okay, this is the solution anyway. Okay. So, we are talking about x 2 being 0. Okay. So, the x 2 is 0 here. So, this equation is 0. I do not have to even look at other things. Okay. Now, what about this equation here? Okay, here you have this x 1 square plus x 2 square, okay. X 1 square is 1 plus x 2 square is 0. So, 1 plus 0 minus 1 is 0. Okay. So, this set of equations satisfy this equation actually. Again similar thing you can do it for this and all that, but in a solution sense again I have to be really careful. For example, okay, if I can demonstrate a little bit, I think most of you know it anyway, but still. Okay, see the solution sense you have to see this particular, for example, either you have to write either something like x 2 equal to 0 or lambda equal to 1. So, you have to see this kind of candidate solution sort of thing actually. Similarly, from that you can talk about this one, this will take you either okay, either lambda is 0 or x 1 equal to no, not lambda is 0, either this no, we cannot talk about that. What you are talking about here, sorry, I just think about that here. This, this equation tells us that that lambda, sorry, again this goes back and forth actually. Okay. This equation tells us that lambda times x1 is nothing but minus half actually. Okay. So, you have to analyze these cases little bit carefully and then put you probably can have some case by case solutions and all that ready. I suggest that all of you do this exercise for I mean in a Longhand algebra sense, so that you will gain lot of confidence actually what you are doing this. Okay, and again I am not recommending at all that you go to this numerical solvers and all that actually, nothing. It can be done in say in pen and paper. It is a fun algebra also to carry out actually. So, I suggest that you do it yourself actually that way. Anyway, so you carry out this and then it turns out to be that these are the candidate solutions. Okay. So, each of the candidate solution now we have to see what is going on. Now, we go back to that whatever formula we had here to analyze. Okay. So, in that setting we have to put it here, what is going on here. Okay. So, we take a first candidate solution probably and then think about putting it all this whatever variables are there, we will substitute the corresponding values actually. Okay. So, if I take the first case actually this particular case, then turns out to be like this. Okay. Then you evaluate this determinant and you evaluate using whatever either first row or first column whatever way actually I am evaluating that using first row let us say. Then it turns out to be like this into this 0 minus 0, this first term minus 1 minus sigma into this term into 0 which is 0 minus this term 0 into 0 is also 0. So, this is this term into 0 minus 0, okay, 0 into this determinant what you see here, sorry, this one this determinant 0 0 2 0. So, obviously, one row is 0. So, this is 0 also basically. Okay. So, 0 into 0 sort of thing. So, that is what it is. Whatever the last term 2 into, okay, this is 0 anyway, but minus 2 into this term actually. So, that is a candidate which is non-zero really. So, that equation tells you that everything is okay. I mean this is 0, this is 0, but this term gives me something like 4 into 3 plus sigma. This is there 2 into 2, 1 minus sign I will take it from here. So, that is 4 into 3 plus sigma is 0. So, that means sigma equal to minus 3. So, what you are getting? We are getting one sigma, one candidate sigma only, and that sigma happens to be a negative quantity. So, obviously, we land up with a case which is a maximum case actually. So, at this point x1 is 1 and 0, we have a local maximum basically. Similarly, I will carry out this analysis for all such points. If you do that, then you will end up with this this table basically. So, this happens to be a maximum. This happens to be also a maximum, this and these two happens to be a minimum actually. Now, if you see this, okay, if these are two maximum, there are two maximums and two minimums, we can always evaluate the function j, again go back and see which is global maximum and which is global minimum actually. Okay, because if the maximum of these two will lead us to the point where the function takes a global maximum and minimum of the two will lead us to a point where the function takes a global minimum sort of thing. So, with this probably I will stop here, but also before stopping I will suggest that some of the concepts I have taken from these two books actually, and this I do not know whether it is available in market or not. You can think about if it is available somewhere in I think Amazon.com or something, you can see that, or there is a good website also that I typically use, which is called bookfinder.com. So, it doesn't necessarily search for only Amazon, but it searches all over the place who are part of that network and gives you some possibility. If somebody is selling a old book or something, you can also buy from there actually. Typically, those are available, used books and all that are also available from those things, and international shipping and all also is possible. And I really do not know whether an Indian print is available for this. It is also a old book sort of thing. But this I certainly know that an Indian book, Indian edition book is available. This Indian edition, but it's a global edition, but there is an Indian edition also available, and it has gone through some editions. That means some error corrections and all must have happened. Some new chapters have come in and all that actually. So, this particular book you can always think of buying. It is not very expensive either basically. Now, this book latest edition, as far as I remember, I know it is 2010, and also remember these books are written for static optimization only. That means, what you have seen here is all this Longhand algebra and all that, are typically not reality, because in many cases the objective function and constraints are large dimension, they are some nonlinear functions and all. So, we cannot keep on doing this. So, it will go to this numerical idea of solving actually. Okay. And all these static optimization books will talk a lot about that numerical optimization schemes. It will talk about various ways of doing things in a proper way, or in an efficient way, or in a less iteration sense. I mean, that kind of ideas will be there. If they talk about line search algorithm, for example, they also talk about conjugate gradient search, they talk about steepest descent algorithm, things like that actually. Okay. So, we will see little bit of that ideas, especially about steepest descent in the next lecture. But this particular book is very useful for those of you who want to kind of develop your knowledge in the static optimization side of the story. Again, many other books are also available. I am not recommending only this, and if you happen to like some other book, it's you are also welcome to see that actually. All right. So, with this I will probably stop this lecture here. Thanks a lot for your attention.